We've been doing a great job at describing what our universe looks like today. We have a model that fits a wide variety of data, but in the last three lectures we tried to dig in a little bit to that model, to the dark energy part of it. The part is that it's an energy density that doesn't change from place to place, that is smooth throughout the universe, and is persistent as the universe expands, is more or less constant as a function of time. What we found is that it is possible to come up with models that explain the dark energy. It could be a strictly positive, constant vacuum energy, one that doesn't change at all. It could be something dynamical that slowly changes, or it could even be a modification of general relativity itself. In each one of these cases, it is possible to come up with a version, some sort of model that actually fits the data. But in none of these cases do we have something that is actually compelling. In none of these cases do we have a specific version and implementation of this idea that is not only able to fit the data, but kind of makes sense to us, is natural in some way, sort of fits together with other things we know. Therefore, in this lecture and the ones following, the next two, we're going to step back a little bit and try to think not specifically so much about the dark matter and dark energy, but about the fundamental laws of physics and cosmology, where the universe came from, how it works at a very, very deep level. But our motivation for doing this is because we want to go back to the dark energy, and to a lesser extent the dark matter, and understand why these things have the properties they do. Maybe it's not so easy as plugging in something that seems to be something that fits the data. Maybe we need to think more deeply about what we consider to be a natural explanation versus an unnatural explanation. So in particular, in this lecture, we're going back to near the beginning of the universe. We're going to talk about inflationary cosmology, the idea that the early universe underwent a period of extremely rapid accelerated expansion. Of course, we've been telling you for the last several lectures that the current universe is beginning to undergo a period of accelerated expansion. So the idea that the early universe had a different period of accelerated expansion doesn't sound so crazy. But inflation came on the scene as a physical theory in 1980 and 1981, and back then the idea that the universe could accelerate was much less accepted. So it in fact predates the idea of dark energy, the idea that there was a phase of dark energy-like domination in the very early universe, and we call this phase the inflationary universe. Now, why do we even think about something like this? For our present purposes, inflation is connected to the concepts of dark matter and dark energy in some very specific ways. First, inflation makes predictions, and among those predictions is that the universe should be spatially flat. Remember, we've talked about the flatness problem, the idea that it would make more sense for the universe to be flat than anything else because it's pretty close to flat already. But inflation provides a dynamical mechanism to make the universe flat, and it makes the universe very, very flat, so that's a very strong prediction. Secondly, inflation predicts a certain kind of perturbations to the universe. Not only is the universe very flat on all scales, but there are also tiny deviations in the density from place to place. And these days we use those predictions when we're matching what we see in the microwave background, the fluctuations at early times, to the observations we have today of large-scale structure in the distribution of galaxies. Inflation, of course, is also similar to dark energy physically. We have some field that is making the universe accelerate, some energy density that doesn't go away very quickly. That's what you need for dark energy. That's also separately what you need for inflation. So by thinking about one, you might better understand the other. Finally, as a spin-off of inflation, we have the concept of the multiverse. We've always known that the universe we observe right now looks more or less the same within what we observe. Outside what we can observe, we don't know what to say. It could be more of the same forever and ever and ever, or it could be very different. We just had no way of saying anything. Inflation at least lets us ask the question scientifically and proposes that maybe the universe is very different outside what we see, and that possibility, the possibility of a multiverse where conditions change from place to place in a dramatic way, will turn out to bear on the question of dark energy. The question of why should the vacuum energy be as small as it is compared to the natural value that it should have. Our expectation for what a natural value is might be different in a multiverse than it is in a single, lonely universe. Okay, so let's think about what people were thinking about back in 1980 when they were beginning to invent inflation, to think about it seriously. The role of inflation is as a model of cosmological initial conditions. The role of initial conditions in cosmology is very different from that of all other physical sciences. If you think about physics as practiced in the laboratory, or chemistry or something like that, what you do is you set up an experiment, you set up the initial conditions. You say, I want to have a ball rolling down an inclined plane and I will put the ball at the top. But cosmology is different than that. In cosmology, you don't get to do the experiment more than once. The experiment is being done as we live right now. The experiment is the whole universe. So a theory of cosmology, unlike a theory of balls rolling down planes or a theory of chemistry, contains not only dynamical laws telling you how things evolve, but also a specification of the initial conditions. Why was the early universe in such and such a configuration that let it lead to the universe in which we see today? That is a respectable cosmological question that just doesn't arise if you're doing particle physics or chemistry. So we have some ideas about what kinds of initial conditions might seem natural or robust or sensible to us. And we have other things that seem finely tuned, that seem like for some reason some particular quantity is very, very small when we might have expected it to be big. Inflation addresses these kinds of questions directly. The entire point of inflation is to make the universe in which we actually see at early times appear very natural. It's a dynamical mechanism from which you can start in various different sets of initial conditions. And what inflation does is get you to a point where it looks like our Big Bang universe, where the universe looks smooth on very large scales with tiny fluctuations in density, very close to spatially flat. So let's see how that works. There are basically two geometrical problems in conventional cosmology that inflation tries to solve. One is called the horizon problem. This is actually the much more serious problem from a cosmological point of view. Think about the cosmic microwave background. Think about this image that we can take from satellites. This is from the WMAP satellite, a snapshot of what the universe looked like only 400,000 years after the Big Bang. Now we know that light travels at a finite speed, 1 light year per year. So when we look back in time, we don't see things arbitrarily far away. We see back to the Big Bang. We cannot see any further back than that. Perhaps we can see to something right close to the Big Bang. We don't really know what the Big Bang itself is, but let's be informal for the next few minutes and talk about as if we can see to the Big Bang but nothing beyond that. Well, the same thing is true for people who would be alive at the time of the microwave background. There was no one alive back then, but imagine an observer sitting at that time in the universe. They would have a past. They would be able to describe certain points in the universe as ones that they can see from signals coming to them at or slower than the speed of light. Other points would have different sets of things that they could see in the universe. But the thing is, you can do the calculation in a universe that is full of nothing but matter and radiation, no forms of dark energy. And what you find is that in the microwave background, widely separated points, in fact, any two points that we observe that are more than 1 or 2 degrees apart, share absolutely no points in their pasts. In other words, you take one of those points and you extend it to the past all the way to the Big Bang. You take another point in the microwave background, extend it to the past all the way, and you get two parts of the universe at very early times that don't overlap. There is nothing, in other words, in the very early universe near the Big Bang that has the ability to communicate with widely separated points on the microwave background. You would have to travel faster than the speed of light. Nevertheless, despite the fact that, as we say, these points were never in causal contact, there's nothing that can get from one point to another slower than the speed of light, these points on the microwave background are at very, very close to the same temperature. What that means is that these different points in space began to expand at the same time. Nevertheless, they were never in contact with each other. So they have their horizons, they have their regions that they can see into the past that don't overlap. So the question is, how do these different points know to be at the same temperature? How did these regions of space know to start expanding at the same time? They were never in communication with each other in any way. That is known as the horizon problem. The flatness problem we've already talked about. If you look at the Friedmann equation of cosmology, it has 3 terms. It has the energy density of the universe, the Hubble parameter, the expansion rate, and the spatial curvature. Basically, if you know what the universe is made of, if you know the stuff inside, let's say it's just matter and radiation, again, imagine there's no dark energy, then you know how the energy density evolves as the universe grows. You also know how the curvature evolves as the universe grows. That's just a geometric fact. And therefore, in the Friedmann equation, the Hubble parameter term evolves to compensate. Basically, rho, the energy density, and k, the curvature, do what they do as the universe expands, and then h just adjusts to solve this equation. The flatness problem is the fact that the curvature term goes away more slowly than the energy density term if the energy density is made of matter and radiation. So if both the energy density and the curvature are non-zero in the early universe, in the late universe the curvature should be much bigger, but it's not. If the curvature were exactly zero, it would stay zero and that would make sense. But why is it exactly zero? Why isn't it some small number or some big number at early times, and therefore a very big number at late times? That's the flatness problem. So these problems were known in the 1970s. They were known to Alan Guth, who was the one who invented inflation, and inflation turns out to solve both of these problems simultaneously. What inflation says is that you start in the early universe with a tiny little patch of space dominated by some ultra-high energy form of dark energy. Because it's ultra-high energy, this dark energy accelerates that little patch of universe at a tremendous rate. It's not matter or radiation. It remains approximately constant density and leads to a tremendously fast expansion rate to this little patch of space. So that means two things. One, this little patch of space that might have had a curvature to begin with has its curvature inflated away by this incredibly fast expansion rate. Remember, curvature goes away, energy density goes away faster if the energy density is matter or radiation. But if the energy density is dark energy, it doesn't go away as fast. So during inflation, the inflationary energy density doesn't go away, but the curvature does. At the end of inflation, that energy density from the dark energy turns into ordinary matter and radiation, which is now much, much, much bigger than the curvature. That's why the spatial curvature in our current universe is so close to zero. It was all inflated away at early times. The horizon problem is solved because you can imagine an incredibly tiny patch of space, one that was in causal contact, one that did share points in the past and had time to communicate, and inflation takes that patch and expands it to a tremendous size. So in other words, inflation changes the past history of the universe in such a way that different points we observe on the microwave background did used to communicate with each other. They were very, very close to each other right at the Big Bang. They did know what each other were doing. There is no horizon problem in inflation. So what you need to make that work, of course, is a temporary form of dark energy, a form of dark energy at very, very high energies that accelerates the universe at early times and then goes away. In 1980, this was dramatic because we didn't know about our current form of dark energy. This was all brand new stuff. But these days, we think, okay, that's something we can make sense of. It was Alan Guth, who was a postdoc in 1980 when he invented the theory of inflation. A postdoc is something in between when you're a graduate student and when you're a professor. You get a series of jobs in which you're supposed to do nothing but write papers and do research, so universities can decide whether or not they would ever want to hire you to be a professor. And these days, you might do 1 or 2 postdocs before you realize either I have a professor job now or I should find other work. In those days, in the 1970s, you would even do less. Maybe 1 postdoc, 2 was unusual. Guth was on his 4th postdoc, in the 9th year of being a postdoc. Everyone thought that he was really, really smart, so they kept giving him jobs, but he didn't write that many papers, so they didn't give him a professorship position. Finally, he hit the jackpot. He invented inflation. He was actually not trying to solve the horizon and flatness problems when he was working on inflation. There was another problem called the monopole problem. There was a set of theories called grand unified theories that tried to outdo the standard model of particle physics, to try to take the strong force, the weak force, and the electromagnetic force that we know and love, and to unify them in a single description. This is a very compelling idea and still might be right, but it made a prediction at the time that seemed incredibly incorrect. That prediction was there were these particles called magnetic monopoles, individual magnetic charges which we don't see in nature, but we do see in individual electric charges. According to grand unification, the universe should be full of magnetic monopoles, but we don't see any. How do you get rid of them was the question that Guth was trying to answer. So not only does inflation solve the horizon and flatness problem, it also solves the monopole problem. You have a high density of monopoles in the early universe. All you do is you inflate them away. Since then, inflation has become a great cure-all for anything that the early universe creates that you don't see in the later universe. As long as those things that were created before inflation, inflation can dilute everything away by a tremendous amount before its dark energy turns into ordinary matter and radiation. So Guth realized that he had a solution to the monopole problem. He already had in the back of his mind knowledge about the horizon and flatness problem, and realized all at once that his idea of inflation solved them all. So he literally, late at night, was working and in his notebook wrote "spectacular realization" and put a box around it, that his idea of inflation could solve not only the monopole problems, but also the horizon and flatness problem. That notebook that he was writing in is now on display in the Adler Planetarium in Chicago. It was a moment in the history of cosmology when we realized that this one idea could solve a whole bunch of problems all at once. So people realized this. People caught on very quickly to the idea that inflation was a great help to the various different cosmological conundra that we had. And of course, among other things, Alan Guth got a faculty job very quickly. He's now a full professor at MIT. One of the nice things about inflation was that it provided predictions. It was a scientific theory, made predictions that could come true or be false. Its strongest prediction was that the universe should be spatially flat, was that the total energy density of the universe should be the critical density. And this is an interesting prediction because it was made in 1980, and throughout the 80s and most of the 90s, it didn't look like it was true. People thought that there was enough uncertainty that maybe the universe did have the critical density, but as they measured more and more about the energy of matter, they found out it wasn't enough. They homed in on the energy density in matter being about 30% of the critical density. So there are two really important things that dark energy does to help the idea of inflation, to boost our confidence that something like inflation is right. First, most obviously, the dark energy provides the extra 70% of the density of the universe that we need to make the universe spatially flat. In other words, by 1997, if you believed in inflation, you were worried. There were some people who were actually backsliding and trying to create models of inflation that had universes that did not have the critical density, that were negatively curved spaces instead of flat spaces. Guth himself never actually went that far. You can invent such models, but they're incredibly ugly. The true prediction of inflation is that the universe should be spatially flat. So in 1998, when the supernova evidence came in that there was such a thing as dark energy, and you could make a spatially flat universe without only relying on matter, both ordinary and dark, it made the case for inflation much stronger. That was a prediction of inflation that came right. And then in 2000, when Boomerang and other microwave background experiments said, yes, indeed, the universe is spatially flat, inflation was, of course, right on. The other idea that was helpful to inflation from dark energy is the very demonstration that the universe is allowed to accelerate. Remember, we have something called the cosmological constant problem. Why isn't the energy density of the vacuum much bigger than we apparently observe it to be? We don't know the answer to that problem, but before 1998, it was always possible that the answer was that the vacuum or other forms of dark energy do not gravitate. That there was something in the laws of physics that says that the expansion of the universe just doesn't respond to things with negative pressure. No one had a good model along those lines, but it was an allowed way to think. And if that had been true, it would be difficult to understand how the universe could possibly accelerate. So the fact that we are now observing the universe to be accelerating right now means that it is allowed to accelerate, and therefore it could have been accelerating at early times when inflation was necessary. In other words, inflation is on much better physical grounds now than it was before. So how do you make it work? How do you invent a model of inflation? Well, for dynamical dark energy, we invented a field called quintessence that slowly changes its energy density as the universe expands. Exactly the same thing is true for inflation. You invent a new field, you call it the inflaton because you have no idea what it is. It's the field that makes inflation happen. It's a field that has a huge energy density at very early times and becomes the dominant form of energy in some patch of space, which then accelerates, inflates at a tremendous rate. This happens and the energy density in that inflaton field gradually diminishes, but very, very gradually, so that the expansion rate is continually accelerating. Then at some point, there's a transition. There's a phase transition where the energy density in that dark energy transforms into ordinary matter and radiation. We call this reheating. In other words, it's a nearly constant energy density for a while, and then it turns into matter and radiation that we know and love. We see that as the Big Bang. That's the basic idea of inflation. So because the physics underlying inflation sounds to our ears very similar to the physics underlying quintessence or dynamical dark energy, some people have asked the question, is it in fact exactly the same thing? In other words, is there one field that was the inflaton at very early times, provided the dark energy back then, and also is now the quintessence field, providing the dark energy right now? And papers are written with titles like Quintessential Inflation. The opportunity for a pun in this field is never passed by. Well, the answer is it could happen. It could be that the same field is responsible for inflation and for the dark energy today, but probably not. For one thing, the energy scales are tremendously different than each other. The energy density of the universe near the Big Bang, when inflation was going on, was many orders of magnitude higher than it is today. It is possible that the energy density was dominated by the same field then and now, but what you have to do is make that disappear in between, or at least be dramatically subdominant. At least from the time of Big Bang nucleosynthesis to the time of today, just before today, the universe was certainly dominated by ordinary matter and radiation. By ordinary, I mean by matter-like particles, including dark matter. We know from the data, from Big Bang nucleosynthesis and from the cosmic microwave background, that the universe wasn't dominated by dark energy all along. The dark energy has kicked in recently. Inflation says the dark energy was dominating way back then. So it's actually easier to make those two periods of domination be due to two completely different fields than to the same field that is important back then, disappears, and then comes back. It's hard to make one field be so different that it dominates at very high densities and at very low densities. But it's still the kind of idea people are working on. It might end up being right. We'll have to go see. The other thing that inflation gives us is a bonus. Not only does it explain away the horizon problem, the flatness problem, and the monopole problem, but it gives us a dynamical origin for the density fluctuations we observe in the universe. If you think about it, the universe on very large scales is in a very strange state. It's very, very smooth on very large scales, but not perfectly smooth. The deviations from smoothness that we can observe, 1 part in 10 to the 5, are certainly observable. They're not absolutely absent. So if you think about it, why would it be that the early universe would undergo some process that made things very, very smooth, but not perfectly smooth? Why isn't it either very, very lumpy or even smoother? The answer, in the context of inflation, comes down to quantum mechanics. Inflation tries to expand the universe and smooth it out. As a universe expands, as it is accelerated by some form of dark energy, that acceleration smooths out bumps and ripples. But quantum mechanics and the uncertainty principle say that you can't smooth out everything perfectly. You're trying your best to make the universe smooth, but the field that is doing it, the inflaton field that is driving the energy density, has quantum mechanical fluctuations, a little bit of jitteriness that you can never get rid of. It is those quantum mechanical fluctuations that turn into perturbations in the density of matter and radiation and dark matter, and those show up in the microwave background as temperature fluctuations, and they grow into galaxies today. In fact, there is a prediction on top of that, namely that the amplitude of the fluctuations should be more or less the same at every distance scale. That's because inflation, as it's happening, is happening at more or less the same rate at every distance scale, and it is imprinting fluctuations as it goes along. This is, of course, exactly what we do observe. When we look at the microwave background, when we look at large-scale structure in the universe, we see perturbations that seem to be about the same primordial amplitude, whether they are 1 parsec across or 1 gigaparsec across. So inflation at least is coming close to being correct with that prediction. The other bonus that we get is a little bit less tangible. The tangible bonus that we get from inflation is the fact that there are density perturbations that are predicted, and in fact it has become a cottage industry amongst cosmologists to think about how inflation leads to those perturbations, where they can come from, and how you can test them. There's a slightly more speculative outcome of inflation, which will turn out to be useful 2 lectures from now, which is the multiverse. We alluded to this at the very beginning. We have this picture of inflation in which there's a tiny patch of space at early times that was dominated by the dark energy in an inflaton field and accelerated at a tremendous rate, grew up to be a universe-sized thing, what we live in today. But back then, what about the other patches of space? What about the other parts of the universe which were not in the little patch that initially inflated to become our universe? Well, it's easy to imagine that there were all sorts of fluctuations, that the universe was very different from place to place way back then, before inflation ever happened. So inflation grabs this little piece of universe, expands it into what we see today. But other regions could easily be grabbed by different kinds of inflation, different inflaton fields, or just the same inflaton field but evolving in a different way. The act of inflation might very well be to take different parts of the universe and to blow them up into universe-sized pieces, but end up in very different conditions. So we need a theory of how the universe could be in different conditions, but inflation allows us to talk about, in a scientific way, the possibility that outside our observable universe, conditions are very, very different. That will change how we think about what constitutes a natural value for things like the vacuum energy, other constants of nature. We will have a whole multiverse, and the possible existence of a multiverse will affect how we think about problems involving both dark matter and dark energy. So the important thing then, once we're stuck with the idea of inflation, or once we're granted the idea of inflation, which is a great idea, how do we know, number one, whether it's true? Number two, how do we make it work? These are exactly what cosmologists today are thinking about in very serious ways. First, we want to test the idea of inflation. We said that inflation makes a prediction. It takes a little patch of universe, expands it enough to be spatially flat, so indeed, we'll expect a spatially flat universe. It also makes specific kinds of predictions about density fluctuations. In fact, it predicts that the amplitude of density fluctuations should be the same at every distance scale. Both of those seem to be more or less true in the universe we observe. However, both of those were conjectured to be true even before inflation was invented. The problem with these predictions, the universe should be spatially flat and the perturbations should be the same amplitude on different scales, is that they're very vanilla. They're not very flavorful. You could imagine that these are the simplest possibilities for what is true, even if you don't have a mechanism for inflation that makes them true. So people imagined that the universe was spatially flat. People imagined that there were different density fluctuations with the same size on different physical length scales before anyone ever invented inflation. So even though they are predictions, they are not unique predictions. One could certainly imagine that they are true without inflation being true. What we want to test inflation is something more unique, something that inflation says is true that other theories don't necessarily say is true. There is one known example of such a thing. Inflation, when it's expanding the universe, has the inflaton field itself and its quantum fluctuations. Those quantum fluctuations get imprinted into density fluctuations, grow under the force of gravity into galaxies and large-scale structure. But there is another field lying around at that time when inflation is going on, namely the gravitational field. The gravitational field will also undergo small quantum fluctuations during inflation. These quantum fluctuations will get expanded to be the size of the universe. So what is the observable form of a small fluctuation in the gravitational field? The answer is a gravitational wave, gravitational radiation, or individual gravitons. Gravitational radiation is something that we are looking for in laboratory experiments here on Earth and haven't yet found. But what inflation says is there should be a background of gravitational waves filling the universe. It is possible, or at least conceivable, that these gravitational waves could be detected by certain special kinds of observations of the cosmic microwave background. Remember that when we look at the microwave background, we measure its temperature. It changes from place to place. But since we're measuring photons, we can also measure the polarization of the cosmic microwave background. If the inflationary prediction of gravitational waves is true, there will be a very specific kind of imprint on the polarization of the cosmic microwave background. We have so far detected that there is polarization of the cosmic microwave background, but our current measurements aren't good enough to test the prediction of inflation. This is one of the things that we're shooting for in future generations of experiments. To improve exactly those measurements, we might be able to verify that either inflation or something very much like it was true in the early universe. That will still leave us with questions. Even if we know that inflation happened, we're still left with the question of how it happened. What was the universe really like before inflation began? How did inflation start? Why did that little patch become dominated by dark energy? And for that matter, what is the inflaton? What is the field that was responsible for the energy density that led to the acceleration we witness in inflation? All of these are good open questions. The good news is that we have ideas for them. The bad news is that they're a little bit past our reach in terms of experimental capabilities. So what we need to do is to think more cleverly about what could have been going on at the time of inflation, and in particular think about how to apply those ideas to things we can observe and test in the universe, so that we can turn inflation from a promising speculation into an established part of our understanding of the early universe.